Okay, hello stats. Welcome back from spring break. I got my camel stuff on. I'm actually making this video out before spring break. Got my camel Crocs on. If you came to the Zoom meeting the other day, you saw me in my camo. Excited to get outside. I hope to get out fishing if the National Guard doesn't shut the whole thing down. It'll be interesting to see what happens over the next week. So I hope you're able to get outside. I hope some things are getting behind us and we're going to move on. So chapter 10.2 is comparing the difference of means. And we just spent, before we got sequestered out of our school and then during our videos, we just spent the last couple of weeks talking about the difference in proportions, p hat 1 minus p hat 2. And we used all of the Z stuff. We used normal CDF, we used Z statistics, Z critical values, and all of that stuff. Well, this chapter is the difference of two means. It's very similar. I mean, there's really not that much difference, except instead of proportions, we're doing means. So we won't technically know the population standard deviation, so we have to use the sample standard deviation, S sub x, which means that we're going to have to use t distributions and t critical values. That's the real main difference, is we're switching it up to t values. Some of the conditions are a little bit different. The formulas are actually easier to work with when you deal with standard deviation. But again, a bunch of the good material is in the reading, so I'm going to have you read. I want you to pause it right now, and I want you to read 645 through 647. The good information is there. And then after you get done reading that, unpause it, and we'll talk about what you just read. Okay, sampling distribution of x bar minus x bar, the difference of two the difference of two sample means. We have some rules about it. Number one, it's approximately normal if. So what they're saying is if you subtract the means, you'll get a normal curve if 1, both samples are greater than or equal to 30, 2, both population distributions are normal, or 3, one of these and one of these. One population distribution is normal and the other fits the CLT. That's stuff we've seen before. The only difference was there wasn't an N2. Sometimes we had to graph these because we wanted to see if the population distribution is normal. So that fits with what we've looked at before. The second thing about the population distribution is the mean is called an unbiased estimator. The sample means are unbiased estimators. So if you have your sample means, this funky little notation is the difference in the sample means. It's always going to center around the actual population mean. So the true proportion, that should say the true mean difference. The true mean difference. So these two means, if you subtract them, you should be right at what the population mean is. And again, we say the population mean is an unbiased estimator. And the last one, the standard deviations can be found if that 10% rule works for both, and you have to apply it for both. So you have N1 is less than 10% of the population, N2 is less than 10% of the population, and when that happens, you have a pretty easy standard deviation formula. And this tells us how much the difference in sample means will typically vary from the difference in the population means if many, many samples are taken. Okay? What I want you to do now, I want you to pause it, go find your alternate examples, and we're going to do who is taller and chocolate chip cookies right out of your extra examples. So here we go, alternate examples. I hope you have this out. Be filling these out after we're all done with this. At the end of the 10.2, I'll have a place for you to turn it in. Right now we're just doing them and filling them in as we go along. Who is taller? The distribution of heights for U.S. adult males follows a normal distribution with a mean 69.3 inches and a standard deviation of 2.94 inches. So this says of all U.S. adults. This isn't even an S sub x problem. We don't even have to do t distributions. I think it's the population numbers. For adult females, the distribution of height follows a normal distribution with a mean of 63.8 and a standard deviation of 2.80. Suppose that a researcher selects an SRS of 30 males and an SRS of 50 females. Let the average male minus the average female be the difference sample mean height between the sample of males and the sample of females. And it talks about some things. What is the shape of the sampling distribution and why? Well, the shape, for a couple reasons, the shape is going to be normal, so you can write it's normal. And the two reasons I can say is both samples are greater than or equal to 30. That's one reason, so we could write that down. And really reason number two is because both populations are normal. So I would put both. Both populations are normal, and it fits the rule. Number two, or letter B, find the mean of the sampling distribution. The mean is an unbiased estimator, so you simply have to take the 69.3 and subtract off the, where's the girl? 63.8, and that should center around the population number. And the last part, calculate and interpret the standard deviation of the sampling distribution. Well, in order to do this, we would have to have it fit the rule. And the rule was, well, we have to have less than 10% of the population, and I'm pretty sure we have 30 and 50 or less than 10% of the population, so it does fit the rule. But you're going to do that standard deviation formula, and it's going to be the square root, and you'll use the male standard deviation squared over, how many males were there? Like 50? 2.94. The mean, I suppose there's 30 males, so over 30. So the square root of 2.94 squared over 30 plus 2.8 squared over 50, and that's your standard deviation. And what that tells you is the difference in male minus female height will typically vary by that number if you took many, many samples. Okay? We're going to go back to the notes now. All right. Oh, we got to do chocolate chip cookies too first. It asked me to do chocolate chip cookies. So here's Chips Ahoy and Great Value cookies. Ashton and Olivia want to know if generic chocolate chip cookies have as many chocolate chips as name brand chocolate chip cookies on average. To investigate, they randomly selected 10 bags of Chips Ahoy and 10 bags of Great Value cookies and randomly selected one cookie from each bag. I mean, in my experience, Chips Ahoy is like up here, and like Great Value or, I don't know. Chips Ahoy are definitely better. Maybe the chewy ones, that'd be good. They then carefully broke apart each cookie and counted the number of chocolate chips in each. Here are their results. So we have our Chips Ahoy number of chocolate chips, and we have our Great Value number of chocolate chips. I don't know. It doesn't look that different. We'll see as we go through it. Let mu1 equal the mean number of chocolate chips in Chips Ahoy, and mu2 the true mean number of chocolate chips for Great Value. Check if the conditions for calculating confidence interval for mu1 minus mu2 are met. So random. You have to check the random condition for both. So you'd have random SRS for Chips Ahoy and SRS for Great Value. And I believe it said they were both. The 10% condition, we have to take 10%. Let's see how many cookies they had. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 is less than 10% of all for both. I think that fits. That's definitely a condition. But now all of a sudden we get to this normal large sample condition, and we don't have enough. We can't assume it's normal. So when you don't do that, what we've done in the past is we've defaulted to the graph. And the nice part about this picture is they drew a graph. So you should have stuff written down in these two spots. Now in this spot, refer to the dot plots. Did we meet the sample? Well, it's not skewed. Let's just analyze Chips Ahoy first. I don't see skewed. I don't really see any outliers. I don't see anything wrong with that graph that would say I can't use a normal distribution. Great Value. I don't know. There's possible outlier here. That one's kind of out there, but I wouldn't call that overly skewed in any way, shape, or form. So because both of these graphs are not skewed, I would go ahead and say, yes, the conditions for normal large sample are met. And really what we fit is I mean, you could circle normal right now. I mean, we hit the normal condition. It's normal enough, it's not skewed, that we can go ahead and say, yes, the conditions are met. All right, let's go back to this one. And we're only going to work on confidence interval today. So what I want you to do, tomorrow will be the significance test portion of difference of means. Today we'll do the confidence interval. So I do page 649 through 654. Go ahead and hit pause and read that. And when you come back, we'll talk about the confidence interval. Okay, here we go. Confidence interval for mu1 minus mu2. Population, this is the actual population of 1 minus the population parameter of 2. We'll have a confidence interval that fits that information. So we have a formula here, and this formula takes a very common, a very recognizable formula, if you will. We haven't always had this value, and we haven't always had this value, but we've definitely had x1, your mean, plus your t star. And again, it's a critical t value because we're not going to know what the standard deviation of the population is. We only have a sample standard deviation. So the t value, what it does is it takes a normal curve again and it lays it out flatter to make sure you encompass all the values that you need, because your sample standard deviation in general is, well, in general it's always smaller than your population standard deviation. So if you don't spread out that curve, you don't encompass enough values in your confidence interval. So I'm going to use this formula, x bar 1 minus x bar 2, and it should be plus or minus for a confidence interval. That's plus or minus t star, standard deviation 1 over n1, standard deviation 2 over n2. And at some point, you're going to have to do degrees freedom with it. You use the smaller of n1 minus 1 or n2 minus 1. And the reason you use the smaller one is you're basically erring on the side of caution. You're making sure that you want to make sure that everything in your confidence interval, if it encompasses what it needs to. And if you use the bigger one, your confidence interval might be too narrow. And this is all provided conditions are met. Remember, these are t conditions for the difference of means. And we're going to do the Katy Perry example right now. So go find Katy Perry and Justin Timberlake. And we'll do all of this. So we have a full out problem here, Katy Perry or Justin Timberlake. And I'm going to do it with you 100% here, so we don't have any questions. So students wondered whose Twitter account, Twitter page, gets more likes on average, Katy Perry's or Justin Timberlake's. The students selected a random SRS of 15 tweets from Katy Perry and a separate random sample of 15 tweets from Justin Timberlake, and recorded the number of likes for each tweet. Here are the dot plots of the data and summary statistics. So based on the graph and the numerical summaries, compare the likes of Katy Perry's tweets for Justin Timberlake's tweets. Include the following items. All right, so I'm just going to put KP and JT here. KP. JT. Well, Katy Perry's, here we go. I don't really see any outliers. I would call it fairly normal. I would call it symmetrical. So I'm going to put those words. Symmetrical. No obvious outliers. I guess I can do that. Symmetric, and I'm going to call it fairly normal. JT's, Justin Timberlake's. I don't know. I would call it kind of symmetric. Symmetric-ish. That's a new word. That's not a real word. Symmetric-ish. but possibly skewed to the, well, it's skewed out kind of to the right a little bit. Skewed right, possibly. But I also don't think either one of those two graphs are skewed enough that I wouldn't do t conditions. I wouldn't do confidence interval. So I think we're good on that. Outliers for Katy Perry, I see none. But for JT, I'm going to put possible at, I don't know, we have a possible outlier here at, what is that, about 13,000. Maybe he had a sweet tweet that everybody was just, man, wow. He tweeted about his dog, and it was really cool because he's got a really cool dog, and bang, there it was. But I don't know. Anyway, and we got it. So we have that. So the center for Katy Perry and for JT, and I'm not actually going to use the graphs. Katy Perry is right there. You might notice that Katy Perry has a mean listed, and that would correspond with that spot, and JT has a mean listed, and that corresponds about right in there. So center, I'm going to put 7193, and for Justin Timberlake, I'm going to put 6393. And the variability for KP, Katy Perry, she has a really small variability. Smaller. And in fact, we can use that, that number up there. Variability, the standard deviation. I'm going to write the standard deviation is 1749. And Justin Timberlake, his variability is obviously larger. You can see his range as well. Katy Perry has a smaller here, which created her smaller standard deviation. But JT's is definitely more spread out, and he's got a standard deviation of 3470. He also has a larger range of values. I'm going to put that range is larger. So that's just some stuff that we've kind of been talking about the whole year, all rolled up into one. So we got that stuff. The next thing is to actually create the confidence interval now that we have an idea of what the data looks like. So I'm going to go down here, and let me zoom out a little bit here. It says, construct and interpret a 95% confidence interval for the difference of mean likes for tweets from Katy Perry and from Justin Timberlake. And I think I'm going to do one of those deals where I get you most of the way there, and then you guys can go in and finish it off. So let's do a 95% confidence interval for, I don't know, let's call it mu of KP minus mu of JT. The true mean number of tweets for Katy Perry minus the true mean number of tweets from Justin Timberlake. So we'll put 4 mu KP true mean number tweet KP KP, and mu of JT is true mean number tweets for Justin Timberlake. All right, and now we're going to plan. Our plan, we have a two sample, and we got to think about this now. This is not a Z interval because we don't have all of their tweets, and we haven't done all of the math of every tweet possible. So we don't know the population standard deviation of all of their tweets. We'd have to go into their Twitter account and run some statistics, which this is not what this is about. This is if we took that sample and we ran the math. So we have this sample size, we have a smaller standard deviation. So because of that, we have to use it's a two sample T interval for true mean tweets. So it's a little bit different. And it's a 2-sample t-interval for, again, it's mu of kp minus mu of jt. And just from a, I don't know, from an idea, I think, did Katy Perry had a larger mean. So I would assume that when I do this, I think I'm going to get positive numbers here. But I also noticed that Justin Timberlake had a wider standard deviation, so maybe it might encompass, it's going to be weird. I don't exactly know how the number is going to end up when I do this. But let's do it. Random. Mu of kp was random SRS, and actually that one, x bar and x bar 2. I should put probably x bar of Katy Perry was an XRS, and x bar of Justin Timberlake was an SRS. I'm going to go ahead and say 15 is less than 10% of all of their tweets, and 15 is less than 10% of all of their tweets. Again, I don't follow either one, but I'm assuming they've all tweeted more than that, so that's just me making an assumption. And the last one, a large sample, not met. 15 is less than 30. But we do check the graphs. And nice for us is the graphs are up, and neither is skewed. So we're okay. That checks out. So our conditions are met, thank goodness. We can do the math. Whew, that was worrisome. All right, let's do the math now. So do. Okay, so we're going to have the average for Katy Perry minus the average for Justin Timberlake. We have that. And then we have plus or minus. Now it's a t-star value. And then it's the square root of the sample standard deviation for, I should put sample standard deviation of Katy Perry all over n, plus the sample standard deviation of Justin Timberlake squared all over n. And that should do it. This one, I'm going to show you where to get those numbers from. When you do this, go up on the chart, get that one. I think that was in the 7,000 range. Go up on the chart. This one is in the 6,000 range. So you're going to write those two numbers down. And then plus or minus. Now that t star, we got to go in and find the critical t value. Now I know the z star is 1.96 for a 95% confidence interval. I think t star is more than that because it's more laid out. I don't remember what it is, so you're going to have to go in and find that. And to find that value, you're going to go inverse t. It's not normal, it's not t CDF. Okay, it's inverse t. We have that right. And your degrees freedom, let's just, I'm going to make sure I do this right here. I want to make sure I'm telling you right. So I'm going to go, it's in that same one. So inverse t, and it asks for area. Okay, let's think about this now. So I know my degrees freedom is 14, but I got to figure out what to plug in for the area. And the area, well, a 95% confidence interval puts me 5% out on the sum of both of those. 5% divided by 2 is 0.025. That's what's going to go in there. And that will give me that little critical value. So for the area, I'm going to plug in 0.025. And I have a key over here, so I'm going to make sure everything's right. And degrees freedom is 14. And make sure I'm telling you right. Yeah, that's the right number. So if you do that, you'll find that inverse t value. You'll find that t star value. And then you're going to go square root of, and the standard deviations you can get from up in the chart. your Katy Perry standard deviation squared all over the number, which is 15, plus the other one squared, the Justin Timberlake squared over 15. And you're going to run through that, and you're going to find your confidence interval. That's what you have to do. And then you're going to conclude. So you can hit pause, make sure you have everything down, but you gotta go in and you gotta find that. And then for your conclude, and like before, where 0 appears matters. So conclude. When you conclude, I want you to write a statement. The interval from whatever you find to whatever you find captures the true mean of mu of Kp minus mu of Jt, which is the true mean difference in their tweets. And also what I want you to do is I want you to discuss whether 0 appears in the interval. Because if 0 appears in the interval, it is likely, especially if it appears towards the center of the interval, if it appeared out on one of the ends of the interval, maybe sampling variability just barely skewed that, made that 0 come inside of the interval, and if we took a different sample, it might be outside of it. But I think there's some merit in saying, okay, if I have this great big this big interval, and 0's bam, like towards the middle of it, well, there's a pretty good chance there's no difference at all in their mean tweets. If it's outside of the interval, if 0, so if like the interval is skewed, both numbers are positive or both numbers are negative, and you have 0 outside of the interval, well, you can be 95% certain that there is a difference in their tweets. But right now, you can go through the math, you can see where the 0 is at, and you can make your assumption and write your statement. Again, I don't have anything for you to turn in today. You just got to watch this video and do the math with me. This will be it. There'll be more coming up where you'll take pictures of this. So make sure it's all filled out, and we'll go from there. All right, thanks.